basically go searching for asteroids and comets. So I asked him to join us. I hope he joins us. And I said, you know, I'm still kind of learning a lot about telescopes and everything, you know, what's best. So I thought if he got, you know, in this meeting and talked to you guys, that might be good. So
yeah, love to meet him. Yeah. You know, Chuck does that exact thing. He records data on occultations of asteroids.
Oh, okay. This guy has actually discovered a bunch of comets and asteroids on his own using public domain imagery. So
okay.
Yeah. So, but hopefully, I don't know if he's going to be a little shy on joining, but he doesn't have a camera, but he's going to just join with audio, hopefully.
Okay, sure. Love to have him. Of course.
Yeah, it'd be great.
So Bob Richard said he wouldn't be in tonight. He's got another Zoom meeting that he's doing, but in the future, he'll try to Zoom in and use a different connection so he won't have any breakup. And he wants to do a presentation. If we want a presentation, he'd love to do a 45-minute presentation to us. So that'll be in the future.
Okay.
Hank mentioned that he's got more artificial star info and Horsehead Nebula information and photos. Let's see, what else is interesting? Editing in DSS, DeepStarStacker. Where that's Hank can do things like talk about those things. Bob had more astro pics. BobG, your friend Rob Matson, and the Newshawk article on Orion there.
So yeah, a friend sent that to me. I thought that'd be interesting for you guys to see. So,
wait a minute.
Does he live in town?
I'm watching Mike try to kill himself here.
Help!
So, I got you permission to show some slides on filters if you want.
Oh, that's right. Yeah. So 5 of us.
Yeah, the Newshawk guys from out of town. I think the article said San Diego, something like that.
Yeah. So did your friend see it in Newshawk or did you see it somewhere else first?
A friend of mine locally who's not that into astronomy but knows that I am saw it in Newshawk and then sent me that link. I'll find it here and put it in the chat.
What's the link to? It's what? What's the link to?
Oh, it's to an article on Orion, how it's sort of a star generator, that sort of thing. It's kind of general interest.
Oh, okay.
Science, astronomy.
Well, what I did, nothing special, but on this camera here, I had previously purchased a bunch of lenses to fit the Wyze camera. So instead of a super wide, I've got like a narrower one, and so.
What's the brand name on the camera again?
WYZE.
Okay.
Yeah, I looked those up on Home Depot. It's amazing how cheap those are for what they do. Isn't?
They actually have a better one now, Wyze 3, which has got more sensitivity, which is almost a see in the dark type of. It's almost like doesn't need like the LEDs. It's got improved sensitivity. So, but I was thinking about trying to use this to see if I could turn it into a planetary camera, because the lens screws off. It's a normal, I forget the diameter of the thing there, but they make adapters for it. It's very similar to the other web cameras they've made adapters for the last 10 years.
If the lens screws off of it, then it probably has a standard lens,
yeah,
either a C or whatever, a T type. And so you could probably get adapters already made for it.
Yeah. So I'm going to go try that.
Okay, good luck. Looking forward to seeing your results.
Well, it would be interesting because if I put it back into the normal Wyze camera mode, then I should be able to monitor things over the Wi-Fi. It's got a Wi-Fi built in. And so when it's converted to a webcam, it loses that capability.
Okay.
But Wyze is coming out with other things too. It's like a little engine that can, because they're coming out with noise canceling over the ear headphones. They've got a Fitbit type watch, and they're all very inexpensive. It's sort of like, you know, I'm just waiting for them to get bought out by somebody and have them jack up the prices.
No, they won't. They'll get bought up by someone like Bose that already has a noise canceling headset out, but it's $300. So then they'll shut down the cheaper one.
Yeah. That's, you know, being in aerospace, you know, you always know about competitors buying other competitors.
Yeah.
So Rob Matson is joining us.
Who?
Rob Matson, Bob's friend.
Oh. Okay.
So that's
Hi,
my
Rob.
voice.
Yeah.
Bob, you want to say hi to Rob?
Yeah, welcome, Rob.
Yeah.
Maybe he's turning audio on now.
Yeah.
Okay, I'm not sure, but I assume Tim would be showing up, but don't see anything. Anybody want to start with, how about pictures? I want to see pictures. What have you guys been up to?
Mine's pretty quick. You want me to show mine, and then Hank's stuff sounds like it'll take longer.
Okay.
Tom, I sent you a bunch of pictures of my scopes and stuff too.
Oh, did you?
Yeah. Maybe you didn't get them.
I don't remember seeing an
Okay,
email about
anyway,
pictures.
you can look for them in your spare time. Go ahead, Bob.
Okay. We seem to have a little difficulty navigating here. So let's see, share. Here we go.
Lydia.
So here's what I've got, M66 that I shot a few nights ago.
Oh, good.
Yeah,
That's a Leo.
yeah, the Leo triplet or whatever. I started earlier and I was doing some things, and then I had set up my DSLR with the intervalometer taking, a bunch of shots. And when I'd get up to stop it from one and process, I'd go, oh, what else is up there? So I looked on Stellarium and found this and located it and just started taking shots.
Could you click on the picture so it gets bigger?
Yeah, that's about as, is that bigger? I mean,
No.
Nope.
Just put your cursor over it and double click on it.
well, I've got it in Paint.
All we're seeing right now is your file explorer. You need to share a different window, I think, Bob.
Yeah.
Oh, okay. Sorry about that. I'm always blowing this. Yeah, sorry about that. Let me try again here. I got to do a, let's see, how do I, no, I don't even know how I, meeting controls.
You have to close the existing shared window.
There we go. Okay, so now, let me try again here. Okay, there we go. Is that working?
Yeah.
Yeah.
Okay.
That's bigger.
Yeah, sorry about that. It's always, yeah, that's a feature they need to have. Maybe they haven't. I don't know how to do it. Is to see what you're sharing, in another little window. So you've done it correctly. But anyway, so yeah, I did this about. I think I had about 60 shots that were about, I think 60 seconds long each, and then darks and flats and bias. This was with that ASI224. Pardon?
That's a lot of work.
Yeah, well, again, it was just automatic. I just set the DSLR and it just starts clicking away, and I just went to bed, you know, and I set my alarm, but I had to set my alarm like 3 times during the night. I was pretty tired the next day getting up and, you know, hauling everything in when I was done. But yeah, M66, I wanted to do, last night I was out, was getting everything ready, and I had just taken some of the Orion Nebula and just about to do the Crab Nebula. And then literally right on cue, this fog just rolled in, you know, just rolled right in. And it was like, okay, all over, you know, around like.
Yep, done.
Bob, did you crop this photo?
Yeah, this is cropped.
Yeah, it's a kind of blurry a bit. That's what I thought.
Yeah, and then when he said zoom in, I had zoomed in more. So I've got, let's see.
Galaxies are generally small, right? So that's always a problem. So what kind of telescope did you use?
That's the same one that that I've been using. The go back up. That's not it. The F5 Orion. I'm sorry, F5 Celestron Newtonian.
Okay.
So, sorry, I'm got to find this now. Oh, the other one I have that's uncropped is a TIFF file, and I'm not opening it with this. So, anyway, yeah, it's. I still could do some processing. I actually spent about an hour or two on my computer day with PixInsight. I had your picture, Henk, from last week, the Horsehead, and but I didn't have it like as in file form, so I just did a screen grab, and then I tried to manipulate it with PixInsight, and I didn't have a whole lot of luck. I didn't.
You're welcome. You're welcome to have the image. I can send it to you offline, the whole raw file. Then
yeah.
You'll be, and see if you can get rid of those gradients, because I'm looking for a tool that can get rid of gradients easily. I mean, I can do it, but it's all manual work, and it's yeah, I'm curious.
Well, in PixInsight, I got smarter on this today, just watching more videos on it. They have 2 methods. There's an automatic gradient remover and then a dynamic one. And the dynamic one goes through a bunch of iterations and stuff. But yeah, send me the raw one and I'll play around with it before next week.
Yeah.
See
what I like about this this picture is that it really shows off the H alpha areas really well.
Yeah, I was surprised. I mean, I've got, you know, besides a little bit of motion. Oh, this is too one of the first set of shots here where I have the PhD2 tracking working reasonably well. So that was kind of cool. In fact, let me stop share here and try something else here. Let's see. So this one, this is PixInsight. So there's yours, Henk, there that I was playing around with. And yeah, I didn't have much luck, but I shot some of the Crab Nebula here too. But I found this thing, which is one of the tools that they have that's pretty cool for removing images. I'm sorry, removing, bad images. And let's see. This one will.
You mean subs?
Yeah. So I'm going to go to the frames that I had for this. Let's see. To find the right date here. What's nice about it is you can actually make videos too with it. I mean, I could just shoot a video, I guess, but so I should be better prepared here trying to find what I did with this. Anyway, there we go. So you take all these images, a bunch of FITS files, and you load them into this Blink or B-Link tool or whatever. And what's kind of cool here is then you can, if you want, I mean, I know something like AutoStakkert or Registax or something will do this for you, but you can just visually, if you want, pick some out. So this is just, going through all the images here one by one. I've already removed a bunch that were kind of bad, that the thing was guiding, and streaking the stars a little too much. But, and it's even got a little bit of processing right in this tool here to, apply histogram to all the images, get a little bit better. So anyway, I'm just monkeying around with all these tools that I've got. So
well, that is a handy feature.
Which camera are you using?
So what is your exposure time for your guide camera?
For the guide camera, I have it set on 3 seconds.
Okay.
And then there's a little gamma function where you can adjust it, and you can either have it auto pick a star to track, or you can pick one yourself. I've been picking one myself, and then there are a bunch of dialog boxes with setups.
I know it's hard when you're out and looking at galaxies because you're not in a star-rich field necessarily like you are in the Milky Way.
Yeah.
But I would try and pick one that has about a 1 second exposure time in the guiding. That might help you get rounder stars.
Yeah, I can do the 1 second. I'm just watching some videos on it. People were saying that maybe that's a little too much update, because this is, feeding the mount with data, a little nudge data, moving around. But yeah, maybe I'll try that. Maybe. But I found something last night, is that I accidentally had the same camera. So I have one USB running into the computer, and then the ST4 cable running into the mount. And then I accidentally had 2 applications. I had both SharpCap and PhD trying to use the guide camera at the same time.
Yeah, they'll fight with each other.
Oh, and I didn't know that. And I was fighting it for about a half hour. And then I go, wait a minute, I bet that's what's happening. And sure enough, I turned off SharpCap, and then the other started working fine, so. But yeah, I'm really liking that guiding, and I'm hope I can get better at it and learn a little bit more how to use it. But I'll try that shorter exposure. I was getting a little afraid when I was moving the things around that I had to get it really precise, or it wouldn't. The camera kept disconnecting and everything, but it was that other problem. So.
I see from your blink thing, I see that you've got a good set of dither on each of the subframes. Yeah,
I have not I have not tried to dither the thing yet. I mean, that's the next thing I've got to do. And I was wondering if just with auto guiding, if it's sort of dithering on its own.
What you've got is something's loose. And if it's a DSLR, then and if the shutter closes, you don't have a permanent mirror up.
Yeah.
When the mirror comes down, it's causing your whole system to do the dither. So it's an accidental dither. And that means something's loose, and it can lead to those streaky stars too, football shaped stars.
Yeah.
So if you're not dithering on purpose, then you should have exactly the same image over itself when you get everything clamped down.
Yeah. Yeah.
Moving.
Well, this is moving because of the auto guiding, because it's not perfect, guiding or anything. And
yeah, I mean, between frames, within frames, you get, because you had some big jumps in there too.
Oh, those are because I removed images and sequence of images, and especially near the end there. But and also the reason I cropped it, Hank, was I saw this light up here and I wasn't able to process it out, so I just cropped it out. That's why I went in kind of quick, kind of close. I was just really happy with the fidelity that I got with it. So
which camera is this that you took it with?
This is the ASI224MC. It's meant to be a planetary. It's just like a 1.2 megapixel.
Yeah.
Lower.
Does really well.
Yeah. So, and I'm still on the hunt for a better camera, but I don't know what I'm going to get yet. I've still got to look around. But
Bob, what is your telescope? It's f5, but what is the aperture?
8-inch. It's an 8-inch Newtonian. Yeah.
And you're using the AVX mount?
Yeah, the AVX. And it's interesting, if I load that other Crab Nebula set of things, you can see kind of how bad the tracking was on that. Even though, I do like a 5-star. First, I do the polar alignment and I get it within like a few arc seconds. And then I do a the 2-star alignment with the AVX, and then 3 calibration stars at least. So I have 5 in there, and it's pretty good at finding things. It centers them pretty well, but it's just, its inherent tracking isn't all that great, you know, over time.
Yeah, and an 8-inch newt is also a bit much for an AVX, actually. That could be also another reason why you have these problems.
The weight, you mean, or?
Yes. So
yeah.
For an AVX, you should probably stay below 6-inch.
Yeah, yeah, and especially if I put a big heavy camera on there. I have 2 cameras. I have the guide scope and then the DSLR. So.
Right, right.
So,
yeah, that's probably too much.
Yeah.
But this was taken with the small CMOS camera, right?
Yeah, I was guiding with the ASI120, and then the pictures of this were actually taken with a 224MC.
Uncooled, right?
Yeah, uncooled. Yeah, it's just a very basic camera.
Hey, Bob, I thought you said this was taken with a DSLR, right? Didn't you say that, or?
No, I'm sorry. These I took. Wait, I was saying that. No, these are FITS files. So no, these I did take with the ASI224.
Okay, sorry.
No, I might have said that actually. It's just last night. It's in my head because last night I was using the DSLR for the first time doing that, and I did say that earlier, but that's same thing with SharpCap. You know, you can just program it to take like take so many 100 images or something. So
right,
yeah. What else was I going to say? No, I don't know. Just keep monkeying around with stuff. And in fact, before this, I was looking outside. It's kind of windy and a little bit cloudy, but when this is over, if it's clear enough, I might go out and try to get the Crab Nebula again. So.
Is your scope permanently set up outside? You just walk out and use it?
Yeah, if any kind of foul weather's on the way, like there might be a little rain later in the week, I'll bring it all in.
At my place, it rained this morning here in Goleta.
Yeah, it looked like it was going to. I was watching for it here, but it never did. So
we got a few drops. So if this is not a DSLR, then it's not jittering because of mirror motion. So I would say that your polar alignment or your tracking is off a little bit.
Well, I know what the polar alignment is. It's within less than 10 arc seconds.
Okay.
So, and what I do is, since I've done that the night before, I still do it. And it's just, whenever I set up the next night, it's really close, you know?
Yeah.
So,
but that may be what the computer says, but it's never anywhere near 10 arc seconds. If you get, 1 arc minute, that's probably good, because the play in the axis of an AVX is probably that much, easily 2 arc minutes.
Yeah. Could, this thing though, when it does, this separate thing, but with PhD2, when it's doing that setup, it's actually testing for backlash and all these things too, which is kind of cool. It sort of filters that out. So
now, the rule I always used is like what Henk was saying. I use 3 arc minutes as the finest star I'm going to get.
Yeah. I just read what the when it shows me the map and everything, it's actually showing you a map and vectors and everything. So, and it moves around too, obviously.
And the other thing you have to keep in mind, Bob, is that this is an iterative procedure. Okay, so if you have an AVX, first you do an alignment, 2 or 3 star alignment. It gives you the go-to alignment. Then you do the ASPA thing probably, or did you use PoleMaster for it? SharpCap.
Yeah, SharpCap, right? SharpCap.
Okay. Then I take it back. No, I used to have use an AVX, and it has its ASPA routine, right? So you first do the go-to alignment, and then you it tells you, okay, point at this star, and it moves it a little bit and say, okay, now use the Alt-Az controls to center it, and then it's supposedly polar aligned, and that is actually the tool that tells you, okay, you've got 0 arc seconds error, which is just a line, and it's also iterative because then you have to redo the go-to alignment and you have to do it again. So, and you can tell that after iterating it, it improves, but it takes a long time. Well, if you do SharpCap first, then you should be good. Yeah.
I tend to use PhD guiding for my alignment, the drift alignment.
But you have
it takes a while.
You have a peer, right?
And I have a peer, but even when I didn't set up, I still have a PoleMaster, But to verify it, I use the PhD guiding to see if the drift is still minimal, and then I tweak it if it's just a little off.
But you have a solid pier, I presume, that basically if you polar align it once, then it should be good for a long time, right?
Now I do. Before I didn't, and every night I'd have to go and realign it because, you know, the normal tripods, they tweak, you know. You take a cover off and put it back on, that tweaks the mount just a little bit. The pier I have probably weighs about close to 200 pounds. It's
wow,
a 7-inch, quarter-inch pipe and big outriggers, and so it doesn't move at all.
So this one I'm loading just to show what the Celestron did on its own. So here's, again, with that same camera, but this is not using a PhD2. And so you can see what's happening with this guy over time. You know, that's, and again, I'm not monitoring it or anything. And the reason I don't have it centered is I had plugged the hand controller through the little plug in, you know, into the USB port of the computer, and I was trying to use PhD2 with that, and it didn't work. So and what it does is it incapacitates the hand controller, the Nexstar Go-To, that just says like bootload on it, and you can no longer use the, you know, up, down, left, right, or make any selections, which is why I switched to the ST4 cable, just going directly to the mount. But you can see this thing was not tracking very well at all. So
well, I think what I see, if I see those stars moving, it looks like periodic error. You can tell it goes up and then stays down and so on and goes up again. So this is periodic error. I guess usually you can compensate for that. The AVX has something for it, but most of the time people say, well, don't use it. It's difficult and gets worse. So PhD should be able to guide that away. And so, yeah, if you have a lot of periodic error, you need PhD.
Yeah, that they have that feature on it, the PEC, you know, thing where it reads it and then corrects, but I haven't done it yet. I've got a good workaround now anyway. So yeah.
That'd probably be a waste of time. So I've never done it myself, but when I read other people talking about it, it doesn't seem to be worth the trouble.
It also appears that your mount probably was not in alignment, because you can see a general thing where it's going in one direction. It almost
that too.
Yeah. I don't know, and I can't remember specifically what was going on that night. I think I did do the sharp cap polar alignment again, but I think it might have been the night where I was walking around and I accidentally sort of bumped the tripod, and I didn't go back and redo the thing.
Here's another thing to remember is when you're taking your exposures, you don't walk around on your concrete patio.
Yeah, no, I don't. I have this out. It's basically in the dirt in the backyard.
Oh, okay, good.
Yeah, so, but yeah, I mean, it's like, again, each thing that I'm doing each night, I'm getting a little bit better at something, you know. So hopefully the images will improve. So
well, it appears that this PixInsight's really nice. It's really bringing out a lot of things. I'm very impressed by how it works.
Yeah.
It's money well spent.
Like, let's see if I can do this here now. Thing you were talking about, Henk, what you can do, close these guys up. So here's this image. This is just fresh in my mind because for the background extractor thing here for gradients, you can bring this guy up. And I was interested in trying to use this for this guy.
Yeah.
And they say, okay, you do a subtraction, and a lot of the guys just say go with the defaults here. So you select this guy and then go like this. It gives you two new images. And this is actually the background. And you think, oh, there's nothing there. But if you do this stretch on it, you can see, oh, it is detecting like a gradient here. And supposedly this is it with it removed or processed. And it did a little bit, you know, but it didn't quite do it. So
Do
you could always do it a little bit more.
Yeah.
Yeah, I'm not sure. Again, this just takes time to figure out how to use these things. And then there's another one. Close these up. We take the same image. They have this dynamic background extraction, and this is more complex. You set up these model parameters. Oh, here we got to click in the image, tell it this is the one I want, and then it actually, you say generate, and it generates these points it's going to model the background with, and you just want to make sure each of these points is not like, on a star or something. And you can modify these parameters and get more of them. And I was trying to do that. And again, I've got to learn how to use this, but this is like a higher fidelity way of removing gradients from the back.
It would be useful if you could prepare this sometime and then show how it actually works, because you're looking at a bunch of stuff. And but
yeah, I'm going through it really quickly. Yeah. So
yeah, it would be nice if you, I'd be interested in seeing how these things are done.
Okay.
It seemed like if you put a couple of X's over by the upper right corner, you probably could compensate for that more.
The funny thing about that, and I just learned that today, when you do that, go like this and you go generate and you go, oh, and you can just click wherever you want them. When you click up here, when they're turning red like that, it means it's too bright. It won't put the X's there. So, it's fighting against you a little bit. So, once these things are, in a dark background, then they're okay.
Well, you could always crop it. And no problem.
Well, but I want to find, sometimes there are gradients, all over the thing and waves and stuff going through it. So you want to be able to figure out how to fix that. So
Bob, what is that glow coming from? What do you think it's coming from?
I'm not sure.
It's amplifier glow. It comes from the sampling circuitry.
Read noise?
Yeah, some cameras, they say they have amp glow and some don't. And I think this one probably does because it's not their highest fidelity camera, but yeah.
Right. It used to be a big deal in CCDs.
Yeah, this is a CMOS camera, so it shouldn't have any read noise.
It does. They do.
Yeah.
Some of them do.
Okay.
Yeah.
Huh.
Other question I have is, Jerry, Bob was talking about using 3 seconds for the auto guider. What is the minimum to use with an auto guider?
I don't know what the minimum is. I've never tried to set it for a minimum, just for a second. Second always to get very good results for me.
Well, you have to get enough light, right? So one of the minimum is that your optical system has to have enough power to drive it. So you don't want to go below 1 second, I think. Most people use 1 second. I use 2 seconds because the pi is not the fastest, ever.
If it's too quick, it'll go after seeing.
That's when I only have a real dim star.
Right.
Yeah.
I up here where it's had a lot of winds going too quickly, it starts traveling on the seeing. So you interspace, you have to interspace it a little bit so that it only sees an average of the seeing.
Another thing that you have to account for is maybe that if you sample too short, that if you have bad seeing, that it can get twitchy. And PhD now has a new feature. I just read about that. They have multi-star guiding. Yeah. So if you have bad seeing, then it all evens out if you use multiple stars, and the errors that you get are going to be smaller, according to the people who used it.
Which one does
your image will still look cruddy because of the bad seeing.
Sorry, I didn't hear that.
Your image will still look bad because of the bad seeing.
Yeah, the image might still be bad. The guiding will be better, yeah.
Would you say, Bob?
Oh, I was asking what software or what tool does the multiple stars?
PhD 2, and it's a development version, I believe.
Oh, okay. Okay.
I'll have to download that. I found out something.
Before you find improvement at that level, you probably have to first work on the periodic error and the polar alignment, because those are two big things. If you have poor polar alignment, then your guiding is also not going to be good. I mean, that's really an important step.
Yeah.
Speaking about
Henk had mentioned ASPA for Celestron. That means all-star polar alignment.
That's right. Yeah.
Okay.
And the idea is pretty neat.
Speaking about programs, AutoStakkert's got a new version that has some improvements on it that I just learned about night before last. And one of them is with that with AutoStakkert, you can do stacking for comets. So DSS has the hooks to do stacking for comets and going on ahead and all that, but evidently they've added more bells and whistles to it, but it's in the beta development one. It's not in the normal release one.
Okay, nice.
Yeah.
All right. Do you want to show should I show my failures? They're not total failures, but since we're doing, I won't take as long, I hope. So let me see. Is that okay, Tom, or?
Sure.
Okay.
Yeah, go ahead.
Okay, so let me share my desktop. Let's see, this is a desktop, I think. It says screen.
So Jerry, how much time would you need for that slideshow?
So Windows whiteboard.
I don't know.
All Windows.
Yeah, my friend Rob is in the chat side. I guess we're not recognizing his microphone.
Okay.
Can you hear me?
Oh,
yes.
Okay.
There's someone.
Oh, all right. You are picking me up. Okay.
Yeah.
So I've been on lurk mode, so I've been listening to everything, but didn't want to chime in because there was too much interesting chatter going on.
Okay.
I think
it's tough.
Oh yeah. Okay.
It's tough to enjoy the program without the camera. Wait, but you can you see what we're doing on the screen, or are you just only audio only?
No, I can definitely see your screen. So you just don't have video of me. I've got audio and I've got all of your display stuff.
Okay.
So I'm looking at Horsehead Nebula right now.
Right.
Yeah, this is the Horsehead Nebula. I showed that last week, and I was hopeful it was just going to be nice, but I got this horrible gradient in there coming in from the upper left.
I have a Horsehead I could share with you that is about probably 1/20th of your field of view. That's just centered on the Horsehead that I took a few years ago.
Okay, well,
it was my first attempt at astrophotography.
Okay, great. Well, anyway, so I have a gradient here to the right as well, and so the question was, okay, what's causing that? So I went back the night after and tried again. This time I moved the camera a little bit because I first thought it was an internal reflection of the camera. So I'm using a DSLR. It's an APS-C Fuji XA1 modified. And I got this. So the angle was slightly changed, and now I've got this. Well, the main gradient is still in the upper left, but now something moved to the lower light. That's totally blurred out. So the next night I tried again, and I came up with this guy. I thought, okay, well, let me just rotate the camera 90 degrees then. So if it is the camera, then I should see something different. And you have to realize, when you get started and you've got a DSLR, you can look at the LCD screen, but it's kind of difficult to recognize those gradients. Otherwise, I would have stopped sooner. But anyway, I tried a few things. First, I tried the same old position that I had the nights before, and then rotated 180 degrees. Well, the gradients just flipped over 180 degrees, so that makes perfect sense, assuming that the camera is internally symmetric and all that kind of stuff. So that didn't tell me much. And anyway, I decided, okay, let's just try this then if I can't get it. And then the gradient ended up in the lower right. Okay, so I couldn't figure out if it was the camera, what would be causing it. Then I thought, okay, well, I have a focuser that protrudes into the tube, and but quite a bit actually. I've been looking at it this night, and it's by about an inch or so, and there could be a refraction about this. So this single spike that you see here, that is a diffraction spike. It's a magnute. It doesn't have a spider. So if it wasn't for that one single object, there should be no diffraction spikes whatsoever. So this must be from the focuser. And then I thought, okay, well, maybe something is reflecting off the focuser. So let me try to rotate the tube in its cradle by, let's say, 45 degrees. And then I'm going to rotate the camera also, so I've got the same orientation. And that was I did that last night. And I got this. So the gradient that came in from the upper left in all pictures is now gone, but it's probably coming in from the lower left, and it's still horrible. So.
And your diffraction spike is straight up and down now.
Exactly. That's because I moved the position of the focuser relative to the stars because I rotated the tube.
Right.
So I rotated it by about 45 degrees, and that's about the angle that you see compared to the other picture earlier. So you can definitely change the whole thing by rotating the tube and so on. But I think what I need to do is get rid of one extender for my camera where I put the T-mount, in the focuser. I'll still have one extender up on that. If I get with 0, then I couldn't pull out the focuser altogether from the tube, and there's no obstruction there. So that's what I'm going to try the next time. And I just measured it. I think I'm just short 1 millimeter. I also went outside and just took that one extension off, and I think it's just a tad short of back focus. So I'll figure something out. I think I can even put a ring of triplex or whatever, a piece of wood, with a jigsaw or whatever, that I stick in between the T ring and the focuser, and that would give me plenty of back focus. I only need a few millimeter, and then at least.
Hank, do you have a dew shield on your Mac?
I looked at a dew shield and I was thinking the same, that maybe something's reflecting inside in the dew shield, so I took it off and it did not make any difference.
Oh, okay.
So, and I also looked inside the tube of the Mac Newt, and I see all these screws sitting there. There's all kinds of screws around the focuser, and they are not blackened. So that's another potential thing. I may have to take the whole thing apart and just put black paint on it. And also right next to the mirror at the bottom, there are some screws from the holder for the auto guider or the viewfinder, whatever you want to use it for, and it's right next to the mirror, and that could also be a source of reflection. So I think if I get rid of that focuser by messing with the tube length and if I blacken those screws, then those reflections should be gone. I can't think of anything else. Anyway, that was my thing about the Horsehead.
You have a central baffle coming out of your primary mirror pointing at the secondary spot on your Mac. Right?
There are no baffles in the tube.
There's none, so it's just the, okay, well, that's probably where you're getting the stray light from then.
Could be, yeah. I also checked the inside of the scope. It's like flat gray, dark gray. It's not really super black. I mean, I could put a black liner on the inside if I wanted to. I think I'll just first try the screws and just see if I paint them, if it makes a difference. Start
with the low-hanging fruit.
Yeah, or actually first the focuser. I think that's the main culprit. And I also don't like that one diffraction spike. If I can get rid of it.
Good problem solving.
Yeah.
Yeah. So, good diagnosing.
Yeah. It's too bad. And now, of course, the moon is so close to the Horsehead that I can't take pictures anymore. But oh well. I'll have to wait until the next new moon. All right, that was my thing about the Horsehead.
Well, Hank, you also had something about your artificial star results.
Yeah, I had, and for what's his name, Roger or Robert? He wasn't there, I think, the new guy.
Robert Richard.
Rob.
Okay.
Or Bob Richard.
Yeah.
Okay. Well, anyway, okay. So just as an introduction of what this was about, I read there was a thread on the Sky Searches, which is an astronomy forum that I'm on, and they were talking about the minimum that you need to work with an artificial star, and so that has to do with interference patterns and all this kind of stuff. And there were some people who've done this based on the difference in wavelength, where certain rays reflected by a parabolic mirror meet up in the focal point, and I tried to but they publish those results without giving any formulas and so on. So the people are Niels Olaf Carlin and Harold Suter, who has a book on, and I have the book here. I could show that. Okay, so he has a book on diffraction patterns, and I can't see it right now. It was on my desk, I think. Well, never mind. Oh, it's right on the underneath. Here it is. Star Testing Astronomical Telescopes by Harold Suter.
Huh.
It's a very interesting book. It's you know, if there's something wrong with your scope, I mean, it shows all these diffraction patterns.
Yeah.
I don't know if you can see this, but you can. He shows different kinds of errors and so on, and he says, okay, if you see this, then you do a star test, and then you know that the optics are pinched or something like that. It's very interesting. So,
too bad Tim's not on. Tim would like that.
Yeah, and then these diffraction patterns, they're all based on simulations. I don't know exactly what kind of software he used for it, but it's it's pretty interesting. And he's cited a lot, this book. So anyway, so he was also quoting that. So I tried to figure that out, and I should share my screen again, I think. I'm not sharing it right now, right? Okay, so whoops. Here, okay, yeah. So share screen, okay. And share. Okay, all right, here we go again. Okay, so here, to investigate that, I wrote some software in Scilab that actually shows these rays. So the blue rays come in from infinity, and this is the reflection in a parabolic mirror. So if you want to be precise about it, this is how all this stuff is done. So the idea is that this point A is the place where you put the artificial star. Oops. And here is the profile of the parabolic mirror, and then these rays are reflected at different places, and you try to figure out if they meet up in an exact focal point. So this is roughly the radius of curvature. It's in an approximation, and the focal point should be halfway there somewhere. And if you do the math, you can figure out path lengths and whatever. It leads to, something like this. So what you see here, this, okay, so the blue rays coming in from the right are from the point A that we were just looking at. It's fairly far away. Think of tens of meters or something like that, depending on the size of the telescope. They get reflected by the parabolic profile, and the blue lines are reflecting it back to the focal point here, or near the focal point. It's not exactly the focal point, of course, because you're not at infinity. If you were at infinity, they would meet exactly in the same focal point. The problem is here, we're not at infinity, and these rays do not meet up in one single point. So it looks kind of like this. The dark markers are the points of equal distance from as the light rays travel from the source to the reflector and then back this way to the right. And here, this is near the focal point. And if you zoom in further, then you'll see that these rays never meet up at the focal point. And this is where my confusion started, because what sense does it make to talk about interference if these rays don't intersect at a common point? There are several wavelengths in between all these guys. And I think I figured that out. So before I move on, what you see here in green, that's actually a reflection from an elliptic mirror. So the thing is, an elliptic mirror for a finite focal distance is an exact reflector. So if you look here, this is an ellipse. You can look it up in Wikipedia. It's got a property that if A is in one focal point of the ellipse and B is in the other focal point, then the total path traveled from this point A to Z and then reflected back to B again is constant for any point on this ellipse. And the angle of reflection, well, it's a reflection, so the angles are always the same, right? But this is exactly what defines the perfect mirror for this problem. If you have a finite distance, for a finite distance, you need an elliptic mirror, and then everything reflects exactly at the other focal point, and everything is in phase. So one way to approach this problem is to take a look at, well, what's the difference between the parabolic profile and this elliptic profile, and try to find the parameters that keep the parabolic profile as close as possible to the elliptic profile, and then look at the distance in terms of the point A, the point B, the diameter of the mirror, and so on. And then you take twice the distance because the ray goes to the left and then back to the right, and that will determine how out of phase your reflected rays are going to be. And that's the approach that I eventually took. So going back to this picture here, the green lines are the ones where the elliptic mirror reflects back. They meet up exactly in the focal point somewhere near there. I think I have one more. Oh, okay. No, this is actually, if you zoom in on the reflection, this is in the plot in Scilab, you can just zoom in, but here are two rays coming in from the right. The green one is from the elliptic, it represents the ray for the elliptic mirror surface that gets reflected back in green here. So the green line here, that's a part of the elliptic mirror. And the blue line is the parabolic one.
Question.
So sorry?
Just a quick question.
Yep.
For the ellipse, you don't have light coming from A, though. You have it coming from infinity, right?
No. They both come from A. So that's the fun thing about an ellipse. It has a focal point. And so the situation is that the source is at A, and for an ellipse of the right shape, it's exactly perfect. So if you have an ellipse that has its focal points in A and in B, right here, or B is just on the other side, reflected around the central axis, then it will be exact. So for the parabolic mirror, this is not exact, of course, because it's to find a distance. It only works if you do that from infinity. And so the question is, what is the phase difference? Anyway, so I figured all this out. So in terms of an approximate formula that you can come up with after a whole bunch of approximations is you can find that this here is the distance, D is the diameter of the mirror, F is the focal ratio, and A is that the x coordinate of that point, capital A, that we were looking at before. So then you look at, like, say, okay, we wanted twice the distance, and we wanted less than lambda divided by 4 for, say, 560 nanometers, and then you end up with a rule of thumb that says, okay, it is 9. So the artificial star has to be further away than 9 times the square of the diameter divided by the focal ratio squared. And this is exactly the same rule, actually, that is found in Harold Suter's book, thankfully. And I also verified these values with the values that I got from what I found in Niels Olof Carlen's article, and it all matches up. So I put the values in a table somewhere, and so here are some cases. So for my Z12, a 12-inch mirror with a focal length of 1500 millimeters, the source ought to be 60 meters away. Am I correct about? Yeah, that's correct. Yes. And for a 6-inch, wait a second. I have a second table. Let me look that one up. That would be better. Actually, that was the example scope. Okay, here it is. Okay, so yeah. So a 12-inch scope, 1500 millimeter, the source at 60 meters. Then the peak to valley values are like 127 nanometers, 121 nanometers. Whereas for the parabolic formula that I had used before, that was based on the intersection with the x-axis, was much larger, and that's not the right way to approach it. So forget about this column.
So these are for a period or a perfect point source.
Yes.
That's placed that far away. So if there's any extent to it, like if you're using a pinhole, yes, or an LED or something, then of course it has to be much farther away than that. Right.
Well, not a whole lot farther away. Harold Suter writes about that. So I think he says that it just has to be, there's another criterion for the size of the pinhole, and it's based on an interference argument. I forgot exactly what it was. I'd have to look it up on the top of my head. But you're right. You have to account for that. Yeah. So this only considers the distance. So if you have an ideal point source, yeah.
Yeah. Okay, good.
So anyway, these values match up quite well with what Suter and Carlin have. So for a 6-inch with 912 millimeter, you have to be about 12 meters away.
Now the source you use can also be if you use a polished ball bearing, for example, and shine a light on that to get your point source, then it's not the distance from the mirror to the ball bearing that you're counting, it's the distance from the mirror to the apparent virtual image that the ball bearing produces that's this distance. So the ball bearing can be closer.
Yeah.
Strong negative curvature of the ball.
Yeah. I actually tried some of this, not for creating an artificial star, but more for collimation and purpose, trying to track something. But the problem with ball bearings is that they're rough on the surface. And so if you're talking about wavelengths, then not much has to go wrong or you're out of phase. And I think that this is not going to work with ball bearings. I have a hard time believing that you could actually do that and get an interference pattern like an airy disk using a ball bearing.
No, we can do it. We did it in the lab.
Really?
Oh, cool. Using old ball. If they're rough, you're using old ball bearings.
Uh-huh. Oh, that is impressive. So I've never tried that. I would love to try it. Yeah. Did you use a laser to shine on it?
No.
Or?
Well, we just did a bright projector lamp, and then a pinhole, and then shone it on the ball bearing.
And you did get an area disk pattern. That's good.
A diffraction pattern.
A diffraction pattern. Okay. And how far away did you put it?
I don't recall. Okay. This was in the basement of the Griffith Observatory where I learned to do mirror grinding. And this was in 1960. And so they were decommissioning battleships from World War II. It was the end of the mothball fleet. And we had all this, or the observatory had all these teakwood planks that were like 12 inches wide and 6 inches thick. And so someone had a source of these things, and they had obtained a number of these beams, and they in an access tunnel under the observatory, they built an optical bench that we could put our mirror on a trolley, and then we could pull a cord and it would run the mirror down the optical bench to get it. The knife edge was fixed. And so right next to us, we had the ball bearing and the light shining right next to your head. And so then we'd run it down there. And so I would say the distance could be up to 10 or 15 meters.
Okay. What was the size of the mirror?
Well, it was whoever was working on their mirror at the time. My mirror was 8 inches, but we had a person working on a 16-inch and another guy working on a 12.5. And unfortunately, the guy working on the 12.5, when he was in fine grinding, he pushed too hard and the mirror hydroplaned off the tool and hit the concrete floor.
Oh, God.
So he was inconsolable.
Okay, well, sorry to keep you hostage to all this stuff. I mean, there's a lot of...
it's okay. It's very interesting.
Appendixes, but it just grabbed me by the throat during the Christmas vacation, and I had to do it. So I'm done. Anyway, it was fun for me at least.
Oh, very good.
So let's ask Rob Matson, what sort of astro gear is he in market for?
Well, that's a good question. I'm mostly interested in deep sky, not so much in planetary observations, although most of my work in astrophotography has been in astrometry for asteroids and comets. So I typically have been using go-to telescopes, online, renting time on them to just try to discover new asteroids, which is fine.
I heard you had a couple of successful discoveries.
I have about 1,200.
Okay, that's a couple.
Yeah, a lot of those were archive imagery from near-Earth asteroid telescopes in Haleakala and Palomar, where I just grabbed online imagery and found things that were just missed by the automated detection software. It's not hard to find asteroids in old imagery like that. Now I would say it's increasingly difficult to find something that hasn't already been refound later by somebody else. So it is difficult to make discoveries now.
So why
I would say that.
Why don't you just continue to subscribe to these telescopes? Because most telescopes have a subscription service, and that way
it gets pricey.
Telescope in your home.
Yeah, it gets pricey, but it is nice to, you know, after I got kind of frustrated with every time I discovered something, it ended up linking to something that was a two-nighter from a month ago from one of the big observatories. You know, it's like I got I'm competing with a 2 or 3.5 meter telescope. You have to be a little bit more clever about where you look and keep track of where they're looking, because at least they publicize, you know, where they took their deep fields and say, all right, I'm going to avoid those areas. Find the holes where they haven't looked.
You know, we have an observatory headquarters here in town in Goleta, Las Cumbres Observatory.
Yep, I've seen their astrometry in the MPEX regularly.
Yeah. They have one that you can sign up for free, but you're at the bottom of the list, and people with funded grants go right to the top of the list and can bump you.
Right.
But you can get time on there.
So what kind of method do you use for that? Do you use asteroid occultation? And if so, do you need a large scope, or can you just use an amateur scope as well? Because like some people do it with an amateur scope. You don't need a lot of light to see occultation, I think, right?
No, occultations would be a very different approach. I've been doing direct observations, so
okay.
I typically, to have a decent chance of making a new discovery, you have to have you need to be able to detect 20th magnitude, and of course that's kind of dependent on sky conditions each night. But so I've been using mostly 24-inch and 32-inch telescopes.
Yeah, I was just going to say that's the category you're in.
Yeah. You know what? I'm going to have to jump back on here. Just figures. My company is pushing a software update on my machine, and it's going to automatically kill me in 1 minute and 12 seconds.
Oh no!
So let it do that, and then I will jump back on, since it looks like you guys are still going to be going for a while.
About 30 minutes.
About a half hour, yeah.
Okay. Yeah. Hopefully this update won't take too long, and I'll jump back in.
Okay.
All right. See you later.
All right. Thanks.
So what else do we want to get into this evening? Jerry, did you take advantage of the clear skies this past weekend? I didn't.
No.
I've been watching too much.
So many other things doing.
Yeah. I was golfing at Sandpiper today.
You were?
Yeah.
Oh,
Well,
okay, nice. Yeah.
You can show that slide set that I sent to you from Bob Gendler.
Okay. Let's see.
I'll try and scan over it and see if there's anything of interest for anyone.
All right. Let me come back here. There we go. And okay, hold on. I will share my screen here. If I can find our PDF. There it is.
Now, this is copyright material from a conference I attended in 2007. And we got Don's permission to present these or look at them and discuss them. And if we have any questions, we can ask him. He, because it's been 13 years since I was at the talk, although, now this is a guy that started Astronomical filters. So, oh, that's right, I can't move them.
Okay, let me know when you want me to move.
Yeah, move. see. Yeah, he's selling narrow bands, which is, of course, oxygen and hydrogen alpha and sulfur. So narrowband filters, keep going. We're going to look at picture and graph view graphs. So these show, go back. These, go back there. This shows, oh, there, stick there. This shows the effects of filtering on the Crescent Nebula with, oh, they call it the bubble. I wouldn't call that the bubble. That's the Crescent. Oh, it's the Crescent Nebula, yeah. A Wolf-Rayet bubble. Red filter, narrow red, hydrogen alpha 9 millimeter bandwidth, 9 nanometer bandwidth, H alpha 6 and H alpha 4. And of course, you can see the background disappearing as you get it. This would be very good for using in our home environment where we have a lot of skylight from pollution, particularly H alpha. I've seen the entire sky imaged with incredible clarity and contrast from downtown of major cities using hydrogen alpha. Next slide.
Jerry, is this only letting through a very thin bandwidth, or is it?
Yeah, that's extremely, yes, it rejects everything out of the, I think the hydrogen alpha light is 6,600 or 660 nanometers, something like that, or 630.
Yeah, 656, I think. Yeah.
Okay, 656, thanks. And so this is letting in 6 nanometers. So it's letting in from 653 to 659. It's very narrow. And the narrower the filter gets, the more expensive they get. But then you can combine them with other images from RGB and you can get a combined image, which brings back the stars. This is the guy, Rob Gendler, that did it at this time out of his garage in Connecticut by wheeling it out the garage onto a set of pre-marked pads on the driveway. And then his homeowners association let him go out and wrap a black cloth over the street light nearest his home. And then he photographed that way. Okay, next shot. Next slide, please. Okay, go ahead. Yeah, this shows in there where hydrogen alpha is. You can't see my cursor, can you?
No.
But see H alpha up in the top band.
Oh yeah, I see a cursor.
Yeah, that's Tom's. That's he's circling the H alpha wavelength. So that's the color you get when you use an H alpha filter. Sulfur 2 is off to the right of that, closer to the infrared. And then way off to the left is oxygen 3 on the in the blue-green area. But of course you don't show that black and white. Okay, next. Now this shows transmission, or this shows light that's out of band, because this is the bandwidth of the filter that you're using. And full width, half max, I'm sure you're familiar with all these kinds of acronyms. But this is a very good filter. It has in excess of 90% in-band transmission, and it has around 1% or less out-of-band transition. So for astronomy, this is, for amateur astronomy, these are very good passband filters. For where I worked, where we took images from space, this band would go out a little farther, and then it would come virtually straight down with virtually no slope to it at all. The bands he's got here are several layers, interference bands, but the bands we used at work were sometimes up to 128 layers of dielectrics on them to get that high transmission and very sharp bandwidth definition. Okay, next slide.
Question on that, Jerry?
Yeah.
In my online search and everything, it says that depending upon the focal ratio of your telescope, you'll use these filters if you try to use like a monochrome camera, and the you know, it gives you, you know, say you have a 4 nanometer, you know, very narrow band, but it'll shift according to the focal ratio. And they say, if you use one too much, I forget if it's high or low on the F ratio, that you know, apparently the filters won't work, but I haven't been able to verify that.
No, that's absolutely true. I can send you some references, so we'll discuss that.
Okay.
All these transmissions and plots and everything are for planar flat filters, optically flat filters, in a parallel beam of light. And when we take pictures in cameras in space, we have to have the objective bring the, you know, that might be an f3 objective. Then it has to hit a Barlow lens type thing. So now the light waves going through the filter are perfectly parallel, or a plane wave. And then when they get past the filter or whatever else we want to do with them, then it hits optics again, and it continues its path down to like an F3 cone. But you're absolutely right. And when they first did these things on commercial cameras, Canon called them spectral filtering. And in really fast, like 50 millimeter lenses that were like f2 or f1.5, they didn't work very well, because as the angle changed, then it works by interference of light bouncing back and forth between the film thicknesses. And if the film is tilted at an angle, the apparent thickness of each film changes with the angle. So if you have it on a surface that's curved, or the light coming in is coming down onto a flat filter in a curved waveform, same thing, the apparent distance of each layer is slightly off. It's slightly different by the angle of incidence. And sometimes you'll get part of the image coming through the center of the lens straight, and other parts coming through the edge, and it gives you a really blurred, really poor band definition. In some cases, you can make it look okay, but for scientific work, people are very finicky about that. Ironically, and as an aside, when we would make imaging things for planet Earth, looking at things, one common thing that most weather satellites want to do is they want to determine sea surface temperature. And the way you get that is through a proprietary algorithm of taking different filter bands of the ocean and the atmosphere right above it, because you have to subtract out the mist that's on top of the ocean. And everybody had a different algorithm for how they would get sea surface temperature. And we had to keep it proprietary from all the other customers. But they were very finicky. They paid a fortune for their particular pass bands to be very precisely defined. And I guess they all sort of worked, which makes me think they didn't have to be that narrow, but they paid a fortune for it. Okay, next slide.
Okay, so Jerry, if I may interrupt, you said these will only work if the light rays come in parallel, but you know, are these the same kind of filters as what amateur astrophotographers are using? Because they use them on the beams that are not parallel. It's after the lens.
That's correct.
Okay.
And what you do is you want to have them at a part of the film or a part of the layer where they come in essentially parallel. I know if you have a primary like an f2 paraboloid, there is no place where it's other than f2. And filters are hard to use in that way. You want something longer focal length to get a more accurate definition. But we're not trying to do detailed, what does he call it when you do the intensity of the light as a function of wavelength, photometry. And so we're just making pretty pictures. So the very high expense, high-tech filters are not what you would use on your telescope. The stuff Astrodon makes for amateurs does work. Luminosity filters, I think, does real well. But that's right. And you can get sometimes weird effect with very fast systems. Mm-hmm. That would be a good thing for you to do your line plots with, is look at a plain sheet of glass as the lines come in from a parabola, and see what the difference in path length inside the filter glass is for a wave way on the outside versus a wave more centrally located.
Right.
You can see the change in color just by, if you have one of these filters, looking at a bright light through it and just tilting it, you can see the color shift sometimes.
Yeah. Okay, next.
Oops.
This is a H-alpha filter, optical density versus wavelength, and it's superimposed on a quantum efficiency for this Sony focal plane array. And here we're at the red end, which is where silicon rolls off. So this is the type of amount of light that you would get in this bandpass. This is not a terribly tight military spec one. This is probably something that you would run into as a in an amateur telescope or for an amateur scope. Next. Yeah, this is what's used when you want to take a picture and make a good color image. This is where you want to look at very specific bands, usually for scientific reasons. And the Hubble telescope has filters like this on there, and they do not form a regular RBG. This is a set that you use for photometry in astronomy. Okay, let's go on. Okay, this is more of the same. Keep going, keep going. Oh no, band. Oh yeah, go back to that. Go back there. Nope, one more.
Oh.
There. This shows the layers of some of the of a typical filter. They're usually all oxides. They're dielectric materials, tantalum pentoxide, silicon dioxide. This just alternates those two layers. And although we have things that have probably a dozen different compositions, and these are very tricky to make because you want, these are thin films, and thin films don't necessarily form the same crystal structure as a bulk material. So you have to, it's a very detailed technology to try and get the film to go down with the measurable bulk properties that you are expecting. If you put it down on a room temperature substrate, when stuff is deposited, it comes down hot and it lands. And if it hits a cold surface, a room temperature surface, that atom freezes right where it hits. And so the stuff is all hitting randomly and what is that where it's not crystalline, but amorphous. So you don't get a good crystal structure. What you have to have is you have to have the substrate, the layer that's already deposited on, you have to have it about between 1/3 and 2/3 of the melting temperature of the material that's coming in, so that when it hits, it doesn't stick. It has enough time and enough energy to roll around and find its partners and shake hands and form a crystal structure. And you don't want it to be, you don't want to make adjustments after each band. You want it to go relatively quickly, because in a 10⁻⁶ torr vacuum, you're accumulating 1 nanolayer of crud every second on the surface, and that'll destroy your interface. So they have to be made pretty quickly. It's a very challenging technology. Okay, next. Keep going. Keep going. Keep going, next one. Yeah, I think there's a lot of, can you show like all the slides at once? Okay, there. This is good, that's what I was looking for. So this shows a 6 nanometer bandpass. That would be, for this one, that would be hydrogen alpha. Oh, it's O3, there it is. O3, oh, okay. Since I see the thing in red a lot, I would expect it to be hydrogen alpha, but it's not. So, and here it is at 3 nanometers bandwidth, and the claim is that you gain 22% of signal to noise ratio. Okay, go ahead. Next. You see the sky is much darker there. Okay. Go ahead.
You gain 22% in signal to noise ratio over what?
over the wider band gap of 6 nanometers. See, oh, that's my cursor.
You mean if you go from 6 nanometers to 3? Okay, sorry, yeah.
See,
filter is like $22,000 more too.
Filters that are military spec can cost north of $100,000 a filter.
Yeah, I bet.
Wow.
Okay, next. Okay, this is more an idealized silicon spectral response, the O3H alpha and sulfur 2. Similar. Oh, they're looking at moonlight. Yeah, the moon is a good blank source. As a matter of fact, when we put a spacecraft up, we look at the moon to calibrate it. We look at the new moon dark side to calibrate it for cold temperature, and we look at the full moon for bright temperature to calibrate our optics for calorimetry and photometry. Okay, next. This is what you were just talking about, I think, Bob. Simple tilts in collimated life will cause a wavelength shift towards shorter blue wavelengths. So you get faster optics may shift the passband off the emission line. So you can actually, when you have filters this tight, they will shift off of the where you want them to be. Okay, so I'm not going to send you references because Tom has this. So this shows the what happens to an O3 emission line for a very good filter when the light is between 0 and between 10 degrees at angle of incidence. In the upper left, they show the definition of theta. Okay, next. Ditto, 3 nanometers. Yeah, we get the idea. Okay. Keep going, a little more detail than we need. See if there's any pictures coming up. Oh, yeah. Now this one, 5 nanometers and 3 nanometers at F3, full as half map, 92% transmission, 92%. So 10-minute unbinned exposure, calibrated dark light, equalized screen stretch in Maxim DL. Okay. I don't know what the point of that chart is. You definitely get a better background here. With the 3 is darker, more contrasty than the 5. You can see the background is darker. But you've also lost a lot of this fainter material here. It's harder to see. Oh, I'm using my cursor, talking to myself. So the left-hand one has a brighter background. The background is less black. The right one is 3 nanometers. It's a narrower passband. Same effect we saw before. Different object. Okay, keep going.
Aesthetically, the left one looks better.
Go back.
That's because of the fast optics, I believe.
Yeah, it looks softer. It's brighter in the center.
Right.
You've got a 5 nanometer. You're letting more light through.
You're seeing dimmer stars also, just,
yes,
comparing one side to the other.
Yeah, because if it isn't a big hydrogen alpha producer, you're not going to see it. So yeah. No, I wouldn't be picking mine based on these charts. I would get the cheaper filter. Okay, next.
The main benefit is not in what the stars look like, but how far the background, the light pollution is reduced. That's the main thing.
Yes,
and
that's the main thing.
See that.
Yeah.
Yeah, no doubt. That's the goal here.
Yeah. Okay, keep going. Go back one. These squares with these numbers KAF, these are different focal length. These are different chip sizes. KAF, I forget who makes that, but these are in Sony cameras. So this is the amount of light that gets in off angle. You see you've lost, you go down from 93% getting straight through because of that tilt effect going through these straight layers with a curved beam. So you get way off of it, but I don't, oh yeah, it's an F5 100 millimeter system. So you lose about almost 10%, 8%.
So you have to compensate that like a gradient.
Yeah,
Right.
yeah. Now at this level, these are also things where they're worried about every little thing for photometry. So these numbers matter. For me, they don't matter because it's going to look good. Next. Yeah. And nitrogen, H alpha, and oh, and N2 lines. Yeah, I've done that. I've never done that. Okay, go ahead. Next. This is a very narrow one, and this is the six nanometers one. On the right is the wider band pass. On the left is the narrower band pass. And you can definitely see that the background is darker and there are way fewer stars. So you're really cutting into things. Okay, I think that's all we need to, I think the rest of the chart is like that. So
is that the little dumbbell?
That one, M76, that is, yeah.
So I'm looking at some.
What's with the Continuum filter? What's that all about?
Red Continuum filter. That's the opposite. It's the opposite of hydrogen pass. It's a hydrogen block, and it lets through everything else except hydrogen alpha. So it's a blocking film on the
anti-filter.
Yes, it's a non-filter. Now the reason you want to do this is because a lot of times when you put a spacecraft up, you have to figure out where you're pointing, and you do that by star patterns. And nebula and other things confuse it. So you want to block out, if you're going to be in a certain region of sky, you've got to block out everything except the stars. And the orientation software looks for star patterns. It does a plate solve. And there's a famous case that happened about 20 years ago where a satellite was put up by Raytheon. We built the camera and put it up, and we got a call back that this thing can't find where it is. And we had put in an ephemeris in memory, centering on 3 stars as the primary course direction finding. And the star would only pick up 2, or the spacecraft would only pick up 2 stars. And after a month of trying to figure out what was going on, we finally realized we had discovered a new variable star, and accidentally one of our 3 orientation stars was a variable, and it was passing through minimum when the satellite tried to look at it.
Wow.
So we're getting better at it now. Okay, go ahead, next.
It'd be like using Betelgeuse last year.
Yeah, right, yeah, when the dust came in, yeah. Okay. That's it. If you want to talk to this guy about anything or have any questions for him, send them to me and I can send them on to him.
Can he give us a discount on Astrodon filters?
I don't think he does that. At the Advanced Imaging Conference, which I've attended almost all of them, they have the last day, in order to keep people there, it's on Friday, Saturday, and Sunday, and it quits at Sunday at 4. But of course, a lot of people take off Sunday to beat the traffic. So they do a drawing to give away things at the end. And one guy who was just new to astronomy in the 2018, that's the last one they had, AIC, he won an $11,000 experimental mount. Wow. It was an L-shaped half of a fork mount for thing. And he just couldn't believe it. And his friend was just, salivating on it because this guy was just thinking about getting into astronomy, and all of a sudden he had this massive mount. So, and they do give away some very nice things. So.
Yeah, you just reminded me, Rob and I and one other coworker a number of years ago, I was begging upper management to go to the AMOS conference, the Advanced Maui Optical Surveillance, in Maui there for almost a week, and that was pretty interesting. That was an interesting conference. So, but yeah, it just popped in my mind when you mentioned that. They didn't have a
Yeah.
raffle there, but
Okay.
So we're pretty much out of time for tonight. Rob, did you have what kind of are you? What kind of gear are you thinking about?
Well, yeah, that's a good question. I know enough about, you know, my degree's in optics, so, and obviously I've been doing astrophotography not for a long time. I've only done a few just like deep sky pictures just to educate myself, but mostly I've been doing photometry, so it's not really the same problem. So yeah, Bob, you know, brought his telescope out to the desert when we went out trilobite hunting. What was that, Bob? Like 6 weeks ago or something like that.
yeah, a couple of months.
And it kind of renewed my interest in getting a scope of my own. And it's hilarious, you know, that I'm almost 60 years old and I've never owned a telescope. I own some very nice binoculars, but I've never owned a telescope because I always felt like, well, I don't live in a dark sky location, and I'm not likely to live in a dark sky location, you know, for a while. But these days you can do quite a bit, even in light polluted skies. So I decided, all right, well, don't be, don't knock yourself out of a hobby just because of where you live.
You know, there are telescopes available in Dobsonian form that are in the 18 to 24 inch diameter range. And you can get those to do imagery by putting them on homemade mounts, or such as a horseshoe ring mount, or putting them on a platform mount and getting them to work on that without investing in the observatory type mounts that you might think of.
Yeah, that's always seems to be the issue if I'm really looking for photons and collecting and staying on target. I can't really go to an alt-azimuth mount because I'm looking at exposures that are 3 minutes, 5 minutes long. But ultimately, I'm going to be limited by the price point for getting a decent like a 4K camera or even a 2K. So it's almost neither here than I've been spoiled. Let's just put it that way. I'm looking through instruments that have $50,000 focal planes.
You on the alt-azimuth mount, you can do long-term, long exposure time imaging with an alt-azimuth mount that tracks, and it has a field derotator.
Oh, okay. Yeah.
Well, it's not a good idea. The problem is that so if you have an equatorial amount, you can polar align it fairly well, but there's not such a similar procedure for alt-az mount. And if you want an auto guider, that's really quite a bit of. I mean, you're asking for more problems by going alt-az than that you gain, really. I mean, if you do astrophotography, you should be looking for an equatorial mount.
Yeah, if I was strictly interested in, getting minimum brightness targets like asteroids or comets, and I wanted to choose where I'm looking, I just say, all right, fine, I'll look at the meridian, and I don't have to worry about field rotation. But for the amount of integration time I'm worried about, but the reality is that I'm probably not going to be looking at that part of the sky. I'm going to be looking well off the meridian, in which case field rotation is an issue. And it sounds like you're right that you can introduce some sort of hardware solution for dealing with field rotation, or you could just bin your exposures and stack everything in software.
Yeah. Celestron makes a field rotator for their cameras or for their scopes, and I think someone else does too. And several of them have alt-az tracking guides that will respond to PhD2 tracking. Yeah, and but it only tracks one star in the field of view. And that's where the rest of the stars slowly rotate around it because it's not equatorial motion. So that's where
so the problem here is that
the rotator is just a clock. You know, it just has to go around all the way in 24 hours.
So the image is going to rotate around the guide star that you're tracking, and it's not trivial that this guide star should be right at the center of the object that you're trying to image.
No, but if you use the field rotator, then you get the whole field unrotated.
Sorry?
See, the guide scope guides on the guide star. But in the main scope, then the field doesn't rotate at all. It stays the same in the frame of the camera because the camera is rotating to compensate for the rotation of the scope.
I understand that. So if the optical axis and the mechanical axis coincide, then you're good. But if not, and then you have to track around. You have to use an autoguider, and the autoguider is not going to be parallel to any of the other optical axes. So it's not going to rotate around the center of the image. It will go rotate around wherever the guide star is pointing at, and it can easily be outside the image, and you get large streaks. So it's just not good.
You're scaring yourself. It does work. I've seen it done.
Okay, I've read a lot about these things. People on cloudy nights have tried.
It's not as carefree as having a good equatorial mount. That's for sure.
Yeah. If you have a plane wave, sure, it will work. If you want to pay, $100,000 for a telescope, fine. But
well, we build them here too, so.
Huh?
We build them. We can beat $100,000.
The
telescope group here.
Get Tim to make one.
The what?
So
get Tim to make one.
Yes, Tim's working.
Do any of you guys have experience with like Celestron's Edge HD field flattener scopes? Whether they're
I don't.
Whether they're decent or not.
The other guy that was not here tonight, there's Bob Richard. He has a Edge HD.
That's right. He has one too.
But those are flat. They don't need, an edge does not need a field flattener, if my memory serves me right. An SCT will. So an SCT is not very good for imaging, but the edge should be pretty darn good, actually. I don't think you need a flattener for that.
Where are they correcting that? I mean, you've got a corrector plate on an on an SC scope anyway, but it's not correcting for flat field. So you're going to have coma in the corners. You're going to have.
Well, there are coma correctors. Teleview makes a range of coma correctors, and
so you're doing that at the prime focus.
At the prime focus, they have to be, I think, 48 millimeters from the prime focus to the back of the corrector lens, and it will flatten the field and it will take away coma on faster systems. And he makes two versions, one for f6 to f3.5, and one for faster than f3.5, and they work spectacularly.
So Rob, let me ask you: are you looking to do like large nebula? So you want the whole field of view to be accurate?
Yeah, I probably have competing wishes that are kind of in conflict with each other. I do like having a wide field of view for surveillance purposes, for finding things, but and that's good also for large nebulae that are kind of cut off, in a smaller field of view system. Oh, there you go, Edge HD.
Yeah, so this is an article that I read a couple of years ago, and I thought I'd go to the site again. This describes the optics of the Edge HD, and it's been a few years since I read it, but if memory serves me right, it is pretty darn flat. So, they're talking about field curvature here. So you may want to take a look at this paper. I haven't read it, but
Richard Berry wrote it, I believe.
Okay. Yeah.
Of course, my concern with a lot of the Celestron, large aperture scopes, 8-inch, 10, 11-inch, is that they're slow. I mean, they're f10.
Well, no, they have a field reducer that'll bring it down to f6.3.
And then
that's better.
Focus, you can get to f2. How do they do that? Where you put the camera right at the primary?
That's where they basically take the secondary off of the telescope and they put a camera in its place. And then
that RASA, the Celestron RASA, is that F2, I think?
Yeah. Well, it's the regular Celestron HD thing. You just take the secondary off and you put your camera there, and there's a company in Arizona that makes that camera and the corrector that fixes the F2 to something reasonable. Yeah. Bob Richard has that too. When he's on here, he can talk to him about that.
Yeah, it's called Hyperstar, right?
That's the old Hyperstar. Name. Yes, thank you.
I remember that name.
Yeah, I just saw an ad for the photon. Hold on a second. I saw here Starizona Hyperstar 8. There's an 8-inch.
Starizona, the company.
So, yeah, that will let you image at f2. So you can either use the Edge HD for a very long focal length, or you can put this thing on it and it'll give you f2. And they seem to be working fairly well.
Oh yeah, they do work well.
Yeah.
I always wonder about how these big survey instruments are able to cover such a large chunk of the sky per night. And then I see that their field of view is huge. You know, they got like a 2-degree field of view, and I'm like, what?
Well, they're making them bigger.
It's like you are not operating at 10. you're definitely going faster than that.
Their focal planes are giant. You know, they have.
Yeah, they are.
A billion pixels or something.
I just looked online. I read today online that the new, I forget the name of it, new telescope going up in space is going to be able to look at 100 times the field of view that Hubble did on the deep field image that it took.
Yeah, the James Webb telescope.
James Webb.
Yeah.
Yeah, I'm not sure.
There's another one also.
Yeah, it's not the James Webb. It's a different one, I think.
Oh, I didn't know that.
Yeah, I know. I didn't recognize the name either.
Well, is it the LSST that you're talking about? That's now called
LSST. But isn't that on Mount Hopkins?
I think this is called the was it Vera
Large
Rubin?
Optic telescope.
I looked at it really quick. I thought it was going to be launched in space, but I could be wrong. I just looked.
That one's going to have, I think, 7 mirrors on it, 7 round mirrors. And it's going to be the equivalent of an aperture of a 27-meter telescope. And it's the 30-meter telescope that's under construction down in Chile.
Okay.
What's the size of the scope that they're putting up on how I guess it would be on Mauna Kea that they've been getting so much grief from the natives?
Yeah, I think they're on the verge of trying to put that down in Chile now.
Just giving up?
Well, I don't know. They keep saying we're going to give up, and then Hawaii says, no, we'll clear the demonstrators out. But it doesn't happen. It seems.
But
it's not like
I'm sorry, it's called the Nancy Grace Roman Space Telescope.
Yeah, that's it. So that's being launched, right?
Well, I don't know when.
Somewhere in the future.
Yeah.
Oops.
And what did you say the effective aperture was for that thing?
Well, no, that's the one I'm thinking of is not going to be launched in space. That's going to be
where that Nancy one. I just a quick article I read. It said it's going to be able to image 100 times of what Hubble did for the deep field. So whatever that field of view is. So that'll be like millions of new galaxies it'll find. So.
Oh, yeah.
Okay, I think we should call it for tonight. Great meeting. And again, I record these and put them on YouTube. If you look up, click on our picture on the homepage of SBAU.org, it'll take you to where all the videos are kept. And at least 2 other people get to see these somewhere. So not a lot of people review these, but but it's there for your reference.
Believe it or not, I'm rewatching some of them.
Oh, great. Good. That's where the hits are coming from. Great. All right. So next Tuesday, we'll do it again.
Okay.
And carry on.
Okay.
All right. Thanks for inviting me to enjoy your crew.
Come again.
Thanks, Rob. Good to have you.
Good night, everybody.
Good night.
Good night.
Good night.
Night.
Clear skies.
Pretty good.